pleasure to talk here. The title is Higgs. In fact, basically the whole talk is here because of this title. I wanted to have this title, but you will see that it's not yet a complete area. You talk about similarities or hope for a dictionary. Certain aspects of the geometry of the modular space of Higgs bundles. But at some crucial point at the very end, we won't have a complete dictionary yet. But I believe that there should be one, and in fact, maybe that will help us understand several important questions. Modular space of Higgs. So first, let me just start with telling you about these tournaments. You might have seen them or not. I know maybe, but they're combinatorial of tournaments. And in fact, the whole mathematical theory started with so he is talking about the mathematical theory of American tournaments, which maybe we could call round robin. So the idea is that you have players, it's some competition, is tennis competition. There is either winning or losing of every game, and then each player plays with any other. So mathematically speaking, we will see that we will model this with a graph, but I think so. Here is his paper, and pretty beautiful already, because on the very first page he makes already up this this generating function for tournaments. We'll see too the same kind of generating functions. So for each vertex, each player, we will have a variable, and we will just evaluate this product. And then you see each term will correspond to the outcome of the tournament, and we will analyze the possible outcomes by analyzing this symmetric function. And amazingly, he was already interested in symmetric functions. He rewrote this into the monomial symmetric function, and he was interested in which of those monomial symmetric functions are appearing. And then he went on, and there is a theory of this. So let me then give you a few basic definitions, mathematical definitions of tournaments. A tournament is just an oriented complete graph. So you take the complete graph on n vertices corresponding to the n players, and orient each edge in one direction for another or the other. Then we will count how many times a player won. So the score of the player represented by vertex is the out degree of the vertex. For some reason, for me, it's kind of unintuitive, but the arrow means that someone beats someone. So the out degree is the number of won games. And there will be two things. If you look at the score vector, which is just the vector of the scores, remembering which player had which score. And the other one now was, for some reason, maybe McMahon's main interest was the score sequence. Because actually he argues on the first page that at the end of the tournament, the result you get is not the score vector, but the score sequence. You are ordering the scores in a non-decreasing sequence, and that will be the result, the score sequence. And okay, so then just to give some more basic ideas, also to see some examples. So a large chunk of examples are the transitive tournaments. So transitive tournament, just by definition, means that if a player beats another player, who beats a third one, then the first player also beats the third one. And so that just means that this gives us a well ordering on this set. So there will be a best player and worst player. And then therefore it's easy to see that the score sequence is going to be 0 for the worst player and -1 for the best players and linearly like this. And in fact, it's easy to see the other direction. If this is the score sequence of a result, then it actually meant that there was the best player, the worst player, and then but there are many other tournaments, of course, and many other possibilities for score sequences. One important class of tournaments for us will be the strong tournaments. The strong tournament just means somehow the opposite of the transitive. Transitive is some of the weakest. Strong means that there is no particular group which dominates another group in the competition. There is no way to partition the players into two teams so that a player in one team always beats the player in the other team. So that's what a strong tournament is. And very nice combinatorial exercise which can show that this implies the existence of a Hamiltonian circuit, which is an oriented cycle going through every vertex exactly. Okay, so that's a nice class for us. And then what's also very nice, and if you see this, you might already start to suspect the relationship perhaps with vector bundles. If you play with stable vector bundles, then you might find this structure quite nice. So any tournament, then you can prove that you can decompose the players into teams, so that every player in group A, group B, in 2, etc. And if you restrict the tournament to the sub-tournament of every team, then that's a strong tournament. So the structure here should already resemble basically something like the maximum filtration of vector bundles, but something more refined having to do with semi-stable, stable vector. And that's exactly what it shows for us. Okay, so let me give you two examples of this. So if the tournament is strong, then there is just only one team already doing this decomposition, and the team is the tournament is transitive, then the singletons will satisfy this. So these are the two extremes. And then the first result, which will also be crucial for us, is funnily enough due to a mathematical biologist, Landau. In 1953, he was interested in animal societies, and with dominance, he was thinking about dominance between two animals in the group. And then he was studying the combinatorics of that. And in fact, he managed to identify exactly which sequence of integers appear as the score sequence of a strong tournament. Or in fact, he was not doing the strong tournament version, he did the tournament version, but and then it's just a bunch of inequalities. The first one, of course, is that the number of games have to be n choose 2, so the sum of the score should be n choose 2. And for any k element subset, but the smallest one, if you take the first k of them, you should have this inequality that the scores should be at least k choose 2. Again, it's all easy to see that they are necessary, and then it's not for any subsequence of such a result. So I will now already give you how this showed up for us. What was the first link between tournaments and as I mentioned, this match first slide. This is a joint project with Goethe, and within this study, this kind of thing.
No, no, sorry.
And this here in the first slide, I just show you some simple objects in Higgs bundle theory, and later, one more slide later, I will show you how it really showed up for us. So I will first discuss some of the simplest semi-stable Higgs bundles that one has studied. So a Higgs bundle is a smooth projector. And for the exact application, we also will have a effective divisor on the curve. Typically, I don't have it, but for this application, and we will look at Higgs bundles, which will be a rank and vector bundle, together with an auxiliary so-called Higgs field, which is a section of the endomorphism under with values, usually in the canonical bundle, but now we will twist it with behavior. So we should think of this Higgs field as a matrix with values in one point. So that's a Higgs model, and there is a very nice natural stability. If you have studied stable vector bundles, for example, in curves, then we use the same definition of stability, but we restrict the subbundles, which we will use the stability condition to the ones which are invariant under the Higgs field. So we will take all proper high invariant subbundles, and then we compute the slope, the degree of the bundle, and if it was a stable subbundle, then we always have to do this, then the slope of the invariant bundle, and so stability allows equality. So you see, this thing actually is not too more. Then you look at a very special class that turns out very important class of Higgs bundles, ones which split into as a direct sum of line bundles, and additionally the Higgs field is not just I guess lower triangular, upper triangular, I'm not sure, but it actually only goes along the above the main diagonal. So the image of the ice line should be in the iris. So bundle, and this also has to be so phi has to be more trivial. And what's nice, by the way, that such linear homomorphism, okay, so it will be like this because this is fixed by a natural sister action. The Higgs bundle you get by scaling the Higgs field is going to be an isomorphic Higgs bundle. You can use this decomposition and some clever automorphism of the bundle, which will send the scalar model. So that's why we like this, because we study usually this sister action on the non-Higgs fields. So this is what we call type 111 Higgs bundles, the ones. And then now, if you think about this stability or semi-stability condition, if we denote by Li the degrees of these line bundles, then we see that we only sum these by the Higgs field will be the ones which are at the end of this sequence. That's for K equals L equals 1 and L. That subbundle will be left invariant. Phi because phi just pushes everything up, but nothing else. So therefore, stability can be checked on these subbundles. These are the inequalities. Now this one is even more similar to the previous one. And indeed, in one particular setup, there will be a correspondence. And this is how the host productivity be just one. And now we need to really non-trivial Higgs field because canonical bundle one of the sections is really twisted with this divisor. Then this one will have sections, and then therefore we will have Higgs bundles, this type. And because of this degree equals 1, then the Li's can only go down by 1. And that will be important for the equivalence. And then we restrict to the case, and that's really because of the therefore the degree is 0. And you may know, or I'm telling you, this is the case when the modular space is typically singular.
Can you explain what this complete linear series of D equal to 3 means? The complete linear series of D equal to 3 in the second to last line.
It just allows us to have a line bundle there.
Not a notation, I'm just confused about it. Oh, it is the degree. Okay.
Yeah, that's the 3 points.
Okay, got it. Okay, thank you.
Yeah. And then this assumption will be important, and you will see that that actually says the modular space is singular, and then soon we'll see that actually at the most singular point there is some very interesting geometry. That's what us to this equation. So it turns out that this is important, and you will see this is also important for the equivalence. So when the degree is 0, that means that the level is at 0. Now the thing actually looks much more like the one for score sequences because all this n and then like get something very less, and actually you can go the other way. It's slightly off, but it's easy to make it right to get the same inequality. Just replace Li and minus 1 minus Li. And then because the Li's have this property that in order for this Higgs field to be non-trivial, you need the corresponding you have section, line bundle to have section. This one is degree 1, so the degree can only go down by 1, and then that means that this will be a non-decreasing sequence of integers, and then you can deduce the score sequences comments on n vertices will be the same. The sequences of degree 0 and semi-stable bundles. Strong inequality, yeah, in the trivial case. Anyway, so this was, this kind of combinatorial thing happens often with Higgs bundles. Okay, I wanted to show you here before I make an example that the transitive tolerance, of course, is the sequence of 0 if you were smooth. The underlying one is the trivial vector one, and this is where we will be studying. So I just wanted to make this, that these kind of observations are done by many people in the study of Higgs. For example, the people were usually studying was the Coprite case and the degree of the bundle was Coprite. In that case, you can also count to this type 1 Higgs bundles, and then you find a similar, or the different kind of combinatorics. And this one, many people with technology collaborating the line again and then working with payment, and now that's something very recent. But anyway, so there is always this kind of combinatorics, and you wonder, is it an accident? Or in general, by the way, you can ask why is there so much combinatorics related to Higgs modular space?
The tournament with this score sequence has a geometric meaning. We have several tournaments with the same score sequence.
There are all the positive tournaments.
No, So these spore sequences are related with this degree sequence of the Higgs bundles. So a tournament, some orientation on your graph, with that sequence has a geometric meaning for.
That's exactly the $8 million question which I referred in the beginning. I don't yet know. So that's the only thing which is basic. I'm going to give you many dictionaries. Because with this question, we don't understand yet what exactly a tool going to mean the Higgs bundle side. And I believe that that's what this book is about. I believe there is one that will be very helpful. So if you have any ideas, please let me know. Okay, so but combinatorics is not inherent. Structures were done in differential geometry, mathematical physics, no apparent reason to have combinatorics around. And my recent feeling, and in fact, if you look at many of those examples, that the reason always for combinatorics is that there is representations. And that's what we also have retained. So tournaments actually have a serious aspect in representation theory. That's why that kind of representation theory is the one which appears on the geometric Higgs bundles, and that I think is the reason tournaments appear because of their relationship to representation theory, which I will show you in the next slide. And it starts with the mechanism. So if you look at the geometry. So what was he doing in his original paper? He looks at this generated function for each pair of layers, each edge of the graph, and then we will expand this product. And what he was saying that he rewrites everything in terms of monomial symmetric functions. It's in like terms, it just means that we collect all those monomials, those score vector, the exponent of that monomial. They have the same set of scores. Therefore, we can just rearrange them in a way. And that's what he was interested in this kind of expression. And he was interested in, for example, the multiplicity, and that's how many times a score sequence can be repeated. Okay, and then he goes on and he does his magic with symmetric functions, and in the paper, pages of results, actual numerical results, how many, what are these multiplicities for I think 7 or 8 years. But for us, let me show you the relationship to represent. So, okay, I just set up the language so that we can discuss nicely representation theory and data. So we will take the weight lattice or the type A and minus weight lattice, which will be z to the n modulo is line, so it will be an n minus 1 bit lattice. It has an action of which is n in this case. The root system is the type A and minus 1 root system is just exactly the possible outcomes. When AI minus AJ, when I is less than J, you can think of these positive roots. These correspond to the case when one player wins and the negative corresponds to negative. So, okay, so here is the root system, and I will, that's what is this about, to show you that this system. Then we can reform it plates. I like the point of view, maybe here, maybe it's only necessary, but here is your fundamental plate. Now we use the fundamental weight to define dominant weight. So we take non-negative integer combinations of fundamental weight, which will give you some inside, and this will give us the dominant weights. What's very nice about the dominant weights that they will contain exactly one representative of any biological weights. So you can also think of them separately. These dominant weights as the violence of this. And then this is going to be our favorite dominant weight for today. Rho, typically below some positive roots for equivalent to the sum of the fundamental weights. So I am a newcomer to this, so I actually think in terms of fundamental weights. So this is the representation corresponding to the vector one, which I believe is actually a very important representation, but surprisingly, it hasn't been studied very extensively. Maybe the extension of Boston, who has some papers about it, but still I believe there is more to understand about this particular representation. So it's as complicated as it gets, because rho is what we say a regular dominant weight. This is inside interior point of the whale arc. It's the smallest one, like that. But that's why I think it's an. And I show you the tournaments are infinitely related to this particular highest weight representation. In this case, like the one of SLN, there is always going to be an irreducible highest weight representation in particular dominant weight. So we just pick this row, and then we will write down the Vega character formula for the genetic function of the weights appearing in the representation. And you have the denominator and numerator. So in the numerator, this first row is the same one as here. But what's going to happen is that if you take rho, then the formula will be more because we have the denominator, the right denominator formula, which marvelously rewrites the sum as a product. But if any your dominant weight is rho itself, then this rho plus rho becomes 2 times rho. This term will just be the square of this. And so if this factorizes a product, this also factorizes as a product, but now the squares. And now you see this identity into this particular dominant weight, which of course now, for us, if you rewrite everything, and we does it tell us that actually tournaments theory notion? So we see that weights appearing in the representation are exactly for vectors, tournaments, dominant weights, the sequences, so the while orbits of the square vectors, and finally, for actually monomial basis in the rho represented by each monomial in this expansion can be identified one-to-one with, well, we chose this root for the any positive root, you have to treat it. The notion we have in representation theory, but again, this is exactly every edge of the complete graph we have to choose. So tournaments in this representation theory, they is just a monomial basis of this particular expression, which therefore always has a dimension which is 2 to and that's what I would like to push this idea that tournaments are really about it. And I show you why we believe that Higgs bundles, particular situation, also have to do with this reference. So this is really was the motivation with Mirko. We were studying this particular Lagrangian in the moduli space of Higgs for the bottom. So we pick, let's say, the moduli space of semi-stable EGL and degree 0 Higgs bundles, and this is crucial. This degree 0, that's basically why I'm working with this. With Mirko, this is Mirko is And then this 4.8. But you will see that this Lagrangian actually lives there. And because it's, I think, will be crucial, actually has to be studied. So what is again a degree? Higgs bundle, it's a figure in Higgs bundle, so we have a rank and vector bundle, and we take occurrence for it's going to be the trace free endomorphism is twisted by the canonical bundle. And this modular space has actually n components, one for each degree. And what we are studying, what I'm studying more recently again, is the topology of what is called the Higgs integrable system, the Higgs, which is actually very easy to define. It's just it can be defined by taking the characteristics of the Higgs field. Then you evaluate that, and you will see that because the Higgs field its values in the canonical function, the coefficients of this answer should be KC. The coefficients are going to be in the various powers of the canonical. So that's the Higgs method. Okay, I'm not really studying summation in this talk, but that's my main interest. And then, okay, and then I have been recently studying upward flows, and in particular upward flows with type 1 Higgs. So these are the Higgs bundle have a C star orbit whose limit point is this type of Higgs bundle. And I'm going to show you a very degenerate case where the type 1 Higgs bundle is actually more or less until then case. But I convinced myself it's very interesting to go through the wall, stable and then non-stable. But in the wall, you will get semi-stable ones. And it turns out that this one, there is a very nice, very interesting semi-stable Higgs bundle where things are already very interesting. So that has to do with the trivial Higgs bundle, the semi-stable Higgs bundle with the zero Higgs field, the trivial vector bundle. And then you can start to think about what we do. The limit point, and then it's going to be very complicated. But if you have one component, which is still nice, the other components will always have larger dimensions, complicated. But one component is going to be a Lagrangian, what we call the bottom Lagrangian. And this is actually very easy to say. So these are the Higgs bundles between 40 and the trivial. Okay, so they will be, when you do theory, you have to take the S equivalence class as such. And so this actually going to be very singular Lagrangian subvariety, but it has a wonderful independent description. You take the Higgs fields, leave just in here stays the trivial bundle. And so the Higgs field will be in here, and two Higgs fields will be representing the same Higgs bundles if in the PGLM GIP quotient they both the same. And what's very nice about this GIP quotient that this is classic. Many people, but then while, for example, when we had representation, we developed a very nice description of this affine line. It's a highly singular affine variety where we understand in the ring level generators and patients. But for example, it's very hard to compute the Hilbert series, and there are many things we don't know about this thing. So this very singular affine variety, bottom Lagrangian, it sits inside the Higgs there. Okay. And then what we noticed that in some nice situations, definitely when the genus of the curve is 2, that this thing will appear, this situation will appear when the curve will be hyperelliptic, but in the genus 2 case, it will be automatic. So when the curve is hyperelliptic, like in the genus 2 case, then one can show that such a Higgs bundle actually pulls back from the Higgs bundle P. And then because O1 pulls back to the 2 case, you can actually show that it goes down the gym, that's really interesting things on the because you want to close function. So the closure is nothing. It can be identified with the moduli space of semi-stable Higgs bundles on P1, which are twisting by open. So that's the situation previously when the collector was twisted by this. So, and that's how we are in the zero moduli space. Okay, so this now is beautiful because inside the heat-chain moduli space there is another heat-chain moduli space, but instead of over C, which is more complicated, we have the P1, and the bottom Lagrangian segment gravity actually is just going to be an open stratum in here, and that's very Then with Mirko, for a project, we started to study how the heat-chain map looks like on this single moduli space. And then when you look at the heat-chain map, one of the most important fibers is the zero where the Higgs field is important. It's a lot about the overall property. It's a retract. In general, it is going to be a retract of the space of the topology included here. You would be interested in the components of this because this is the top Betty number of the space. And then here it is going to be the nilpotent cone in this moduli space, which in this distinct case will only have the components will only be determined by precisely by the components of stable type 1 or 1 Higgs or P. So that's why we do that. The components of this bottom Lagrangian over 0 is exactly type 1, 1. Stable, it's important. And therefore, they are enumerated by the score sequences. And this is, by the way, how we check. Because as you do, sometimes you have sequences, you want to understand these numbers, and you find which is usually the strong hands and numbers. And then I started to learn more about tournaments. I suspected there is no. So then by now we understand that. Yes. And instead of telling you the reasons why I believe that the modulus space is understood right, instead I just tell you this is as an expectation. So because of many other things, but also because it's likely supported by this community, I expect is that the heat-chain vibration reflect the representation theory of this particular representation. Then more generally, you should see that you could see that I already changed the PTN. Yes, there is an inherent Lagrangian and so in general, you would want on the bottom Lagrangian of the G-check Higgs moduli space, the Higgs system here should reflect the representation on Higgs. Each G, I can take that sum of and by the way, and at the end, I just want to say that this is one aspect which I have been studying in terms of system curves, and that holding the really non-trivial combinatorial process, I do, has a beautiful relationship to the Higgs moduli. Anyway, so this we just take as a motivation, and from now on, I'm just going to talk about ignorance again. But this is the reason I'm talking about because of these expectations and what I hope we can do better questions. Exactly to answer your question. What do varying Higgs bundle theory can I see? So now I'm just going to have fun, and I will generalize tournaments to any root system, and then I will apply folding to these generals. So now we will take any finite root system, which is going to be just from lattice R together with an action I group, X, Y, W. We will remind us how do we positive. We started from it that we fix out exactly one of each pair. And if it's satisfied, the two, and that sum is a root, then that is. So we just weaken the definition of positive roots. We don't want the second property, just the first one. We want to pick from every point. And then it's kind of abstract, and you will see in the beginning there is not clear what to gain. Translation. So, for example, we have positive roots, and they give us positive. It is crucial in our dictionary to the code. So, I mentioned that this actually showed up before this notion, and it was done by even a combinatorial proof for their denominator entity, which is slightly similar, but it's just using this combinatorial. This was inspired by a proof in Gessel. There's some beautiful combinatorial. Okay, so then we are interested in this particular. And then real character, again, just as before, is exactly given by, instead of minus, we will have plus. And again, for each term, without a synchronous movement, we just have every monomial in this expansion. The monomial themselves signal the score vector, and the bilog is dominant. We can then discuss our tournaments, the model for this the score vector. Think of the score vector. Okay, so this is all abstract, and then there is nothing more which has been. Again, because of the Higgs bundle story, I studied this folio. I show you that you can make a lot of stuff. See that you have to do the tournaments to get from one system to the other. So folding is used to.
In the type A case, the classic case, the multiplicity of a weight is that ns.
That's a very complicated thing, right? That's the multiplicity. That's the crucial thing in our project here to understand the multiplicity. And that's where that's what I really understand. The multiplicity, because if you can understand what does the multiplicity correspond to, then you have a shot at finding this relationship to two elements. Here in the tournament, it's easy to say the multiplicity are exactly the tournaments given score. That's the
number of tournaments of a given score is the multiplicity of
the multiplicity of the weight.
That's what I mean.
So in the AM case, the tournament was just an oriented draft. Can you give a kind of a similar description of the BN case where kind of sign draft orientation?
That's what we will do in a moment. It's not to do folding. But there are actually efforts to this direction already in the literature. Yes, but I show you. So let's do this folding. So the folding is a process where starting with the root system and then what is called the linking diagram of morphism, we will produce another folding root system. So we have a setup with the same, but now we have a linking diagram. Okay, I'm not going to say what is linking diagram. Root system somehow inherent automorphism. It's usually not part of it. It's and now there is a very non-trivial combinatorial procedure, which to such an automorphism will produce a new. It turns out that actually several authors, the original combinatorial procedure was this. Why? But in that case, the procedure doesn't. Except in that case, what you will do is that you take the invariant you will take each biology of roots, not biology, by making them the ultimate. Typically, an evolution sometimes we take an orbit of roots and you just take the sum of those in the orbit and that you lie in something. That A2 case is already using roots. But there's a conceptual defining property, and that's the one we need. And then using we and the other and the ring. First to the root system, you take the Lagrange over, you let sigma act on the you will get this subalgebra, and you take then the Lagrange back, and the Lagrange with the algebra. This will be a reductive Lagrange. That's the one which is given. So amazing that you will see when we play with the tournament. Lagrange and now here are the examples. So these are the examples of possible linking automorphism which have non-trivial automorphism. And so this is nice. This is the argument. So the reason is because there is an orbit which contains that the rules there. But then there is Dn, we can flip this through, and then and here are the linking. Thinking that one. But beautifully, Dn, for example, is not yes. No one of them is not. Maybe this one. Yeah. But what really matters is the Lagrange, which is nicely defined. Okay, so let me show you now, starting with the tournaments in type A, using first this one, how you get to Dn tournaments, and then and tournaments you have. So that's the last thing to do. You will follow tournaments. So we will take have an involution, we will do this next involution, which really is involution, something like that. And we will think of the orbits, which is always so now we have n couples playing a tournament. Everyone plays. Everyone, and we will call such a tournament marriage rights. We're talking about our tournaments that left invasion in and those are the ones that's a nicely balanced among the tools. And that is you can actually think about what should be the score vector. There will be, of course, a linear score vector, but we have score vector and be two. If two more, twice as many variables, we have xi's and yi's. But in fact, inside the couple, you know that they will be playing n minus on other couples, and because of the property, the sum of their reasons have to be n minus 1, plus they will play each other. And so you will get 2 n minus 1 is the same. So the score of an element of the couple is always the score. They actually are equivalent. And what we do is that we just take the lower one of each couple and reorder them. And then this is what you can call a merit balance tournament. And then it's a nice thing to work out. That it actually gives precisely merit balance tournaments, give precisely the abstractions where the okay, what you can very nicely see is the generating function. So here is the generating function of merit couple tournament. So when we take this is think of there is not limits. And two players from different couples play with either both sides or both husbands or one husband. No possibility, and so that's the explanation. But if you set here y equals 1, then it's nothing but the Meyer character formula for this particular. And that shows the precise feature. So, and again, everything works out very nicely. The score vectors manage the tournaments in this particular patient, and score sequences of LB tournaments, which are these the dominant weights. And what's beautiful is that in this tournament description, you can see both the symmetry. So that you take the symmetry permutations which leave couples invariant of Bn. And also what's beautiful is that we can say which are the short ones. So the gains between the spouses will precisely correspond to the short ones. Okay, so we actually, this last point we can use, and then I will turn to the last slide to do one more folding, which is more involved, because what we just started is already trivial, and that's the folding. So here, first we will have to be inspired by the Bn case to explain, to get a formula, to get a tournament. So what we will do, we will imitate Bn tournaments, but we will remove the short. So if you know that this is the same. And short roots removed means just we don't let the couples play, the spouses play each other. That's it. So we will have another type of tournament where spouses don't play each other in the couple, and everything is the same. It's still a magic balance tournament, but because you see that. But somehow the ones which we develop a group are the ones which we London. Let's think in terms of the transit. So the Y group is related to positive. So you can think about positive roots. The set of positive roots that's the Y group. And if you just split one of them, then you can find a quantity which doesn't change as course. Anyway, so there is a reason that we investigate this way, because this is the value. There is still one more input. Just flip one of the pairs, and that turns out to be like to be the and just to see, we get this is now our generated function. We don't have the first term because houses each other, and then the d and y of their formula will actually be removed. So now here is this other involution that's thrown out here. That's just flipping, or let us flip the and that's going to correspond to the information. And then we can find this little layer. It will be a singlet one, and then we will n minus 1 layers, one single guy, and n minus 1 couples. So now the new sigma, the induced, which is the induced of this portion, is again the same symmetry, but now there is a singlet. So we have n minus 1 couples, singleton, and now, okay, it's maybe a singlet, it's a marriage balance. Okay, is again a marriage balance tournament where everyone plays everyone except the but we have a single player, and the single player plays twice with everyone because it comes from these points of the neighborhood. And then again, now you can think about this double play will allow to think term which is actually part of the mind. Anyway, so you could do this, and then what's very nice is that the last folding, which we can handle this way, the difficult one, could now also be understood. So that's all. What is the moral is to show you that tournaments have the same kind of relationship to the representation of the underlying algebra to this particular 1-0, and they relate the same way to foldings as you expect from Higgs bundles.